Okay, so now we know how to get mass percent information from a combustion analysis, but how do we go to a chemical formula from that mass percent information? Well, we can determine not directly the molecular formula, but at least the empirical formula, starting with the mass percent information for the elements following this process. So if I have the mass percent data, it's easiest for me to determine this empirical formula by just assuming that I have a 100-gram sample of that material. Now, this does not have to be true at all. It's simply the math works out the same, regardless of whether we use the actual original mass of the sample or if we just assumed that we had a 100-gram sample. The convenience of using a 100-gram sample is that whatever because percent is out of 100, if I have a 100-gram sample, it means that my percent becomes the number of grams. Once I have the number of grams of each element in this process, I use the molar mass of each element to determine the number of moles of each element. Once I have the number of moles of each element, and we've actually determined this along the process of finding the mass percent. But if we're given mass percent values to begin with, this is how we would get there. But once we have the number of moles of each element, I can find the empirical formula. I can find the molar ratio by dividing all of the number of moles by the smallest number of moles, and that will get me a molar ratio, which corresponds to an empirical formula. Let's do this in an example. So first case, ascorbic acid, which is also known as vitamin C, contains 40.92% carbon, 4.58% hydrogen, and 54.50% oxygen by mass. So these are my mass percent values. What is the empirical formula of ascorbic acid? Very first step, I start with my mass percents, and I assume that I have a 100-gram sample. If I have 100 grams, then 40.92% of that is 40.92 grams. 4.58% of 100 is 4.58 grams, and so on. So now I have mass information of each element. Now I convert each of those to moles by simply using the molar mass or atomic weight of the element. So using the molar mass, 40.92 grams, divided by it's 12.01 grams is equal to 1 mole. So that's now a conversion factor. Grams goes on the bottom. Multiply this through, and I come out with 3.407 moles of carbon. Do the same process for hydrogen, same process for oxygen using the appropriate atomic weights or molar masses for each element. And now I have moles of each element. Now to find the molar ratio, I look at these and I determine which of these is the smallest, and I will divide all 3 molar amounts by the smallest number of moles. So here, I determine the simplest whole number ratio by dividing each number of moles by the smallest number of moles. In this case, oxygen is my smallest number of moles. So if I take the molar amounts, the amounts in moles for each of these, and divide by the smallest number, which is the number for oxygen, I come out, of course, with just 1 for oxygen. It comes out to be 1.33 for hydrogen and approximately 1 for carbon as well. Now, that's the ratio, but these aren't whole numbers. 1.33 is not a whole number. So what I have to do after I've done this is I need to multiply those ratios by some scaling factor to ensure that they're all whole numbers. In some cases, they will all come out to be whole numbers when you divide by the smallest number of moles. In this case, it didn't. So I want to look at those numbers and say, what number could I multiply by to get that to be a whole number? Well, 1.33 is, that 0.33 is about 1/3. And so if I multiply by 3, that will then come out to be a whole number. So I multiply all 3 of these ratios by the number 3, and I'll come out now with whole numbers, 3, 4, and 3. These now correspond to the subscripts of my empirical formula. So the empirical formula now becomes C3H4O3. It may seem like a slightly long or maybe even complicated process, but if you follow this process step by step, and you only divide all of them by the smallest number when you're at moles, and then you multiply, if you need to, all of them by one number to get them all to be whole numbers, then it will make the process very straightforward. Let's go through another example. So again, in the last problem that we had done, we determined the mass percents for carbon, hydrogen, and oxygen in valproic acid. And we got them to be 66.6%, 11.3%, and 22.1% respectively. So what's the empirical formula for valproic acid? Well, I follow the same process. I start with my mass percent. I assume that I have 100 gram sample. That means that my mass percent is just a number of grams. And then I convert that number of grams to moles by dividing by the atomic weight of that element. So 66.6 divided by 12.01 grams. Remember, 12.01 grams is equal to 1 mole. It's a conversion factor. I come out with 5.545 moles of carbon. I do the exact same process for hydrogen. Mass percent becomes mass. Divide by the atomic weight. That becomes moles. Oxygen percent becomes weight or mass. Divide by the atomic mass, or the molar mass in this case, and I get to 1.381 moles of oxygen. Now I am at this point, moles of each element. Now that I'm at moles, I will divide all three mole amounts by the smallest number of moles, which in this case is clearly oxygen. So I divide all of them by 1.381, and I come out with there being whole number ratios, in this case for all of them. So that ratio comes out to be 4 for carbon, 8 for hydrogen, and just, of course, 1 for oxygen. Since I have all whole numbers, I can simply write the formula at this point as being C4H8O.